In this video, I'm going to talk about how the buoyancy force on any 2D shape in a liquid is always zero. Whenever you think about the 2D cross-section of a 3D shape in a liquid, for example, if you have a cylinder vertically in water and think about the circular cross-section, all the forces on the walls of that circle all act inwards and they all cancel out so that there's no overall sideways force. And this makes sense for the circle because of how symmetric it is. But the interesting thing is that no matter what shape you have, it can be any sort of random 2D blob. If you think about the pressure exerted on this 2D slice by all the liquid around it, it will always add up to be zero. And this makes sense because when you put an object inside a liquid, the object never feels any sideways force. It only feels force upwards and downwards. So let's say the value of the pressure at this specific depth on this specific 2D shape is equal to P. Then if you consider all the normal vectors pointing outwards along the shape, the force vector caused by the pressure at each point will be equal to negative P times the normal vector. And if you add up all the different force vectors, what you're essentially doing is taking an integral. And you're going around a whole loop. Let's call that loop C. That means the sum of all the different forces, when you integrate them together, will be equal to the closed loop integral around C of negative P times a small normal vector. Negative P is a constant, so you can bring it outside the integral, and what you're left with is this. And our goal now is to show that this integral here is equal to the zero vector. It doesn't equal to the number zero, it equals to the zero vector. And showing that would prove that no matter what shape it is, no matter what specific C we have, the sideways forces are always equal to the zero vector. So now our goal is to show that this integral is true. And to do that, we can consider all the small tangent vectors dl along the curve. If we think about dl going anti-clockwise, as I've labeled here, then all the normal vectors pointing outwards would just be a 90-degree rotation of the dl tangent vectors. And that means we can write that dn is equal to something times dl, where that something turns out to be a matrix. And the specific rotation matrix we need in this case is 0, -1, 1, 0, reading down the columns. So now this integral here becomes the integral along the boundary of this matrix times dl. And this is quite an unconventional line integral, because normally with line integrals you're doing a dot product and you're summing up scalars. In this case you're applying a matrix to this dl vector and you're summing up all the different vectors. Again, our goal is to prove that this integral equals 0. The big insight here is to recognize that integrals are basically sums. They're just sums of infinitely many things. And because matrices are linear transformations, they're part of linear algebra, when you have the same matrix applied to many different vectors in a sum, you can factor out the matrix. And it's the same as having the matrix being applied to the whole sum, or in this case, the whole integral. So here you can just factor the matrix out of the integral and end up with 0, -1, 1, 0, times the closed loop integral around the boundary of just dl. Again, this integral here results in a vector. You apply this matrix to that vector, and what you end up with is the overall sideways force, which we expect to be 0. And we can show that it's 0 by considering this integral here, the integral of dl around this closed loop C. What this integral is saying is add up all the different small dl's as you go around the loop, and the value of the integral is where you end up once you add up all of these small dl's. Well, because it's a closed loop integral, you end up where you started, and so this integral must result in the zero vector. That means you're applying this matrix to the zero vector, and whenever you apply a matrix to a zero vector, you still end up with the zero vector. So there we go. We've shown that by considering the forces as a line integral around the curve, and thinking about normal vectors as a rotation of tangent vectors, we can prove that the sideways buoyancy is always equal to 0. So thank you for watching this video. See you next time.